Hi everyone, this is Janice Connell and this is my Lab 2 video for physics at Georgia Tech University. We were to observe the motion of a falling object. We were to use Tracker to gather observational information, and we were to construct a computational model using Python in two ways. One, using gravity only as an impacting force, and two, using gravity and drag as the impacting forces. We were to compare the two models' results to the observation results. My video was of a wadded up piece of paper towel dropping from a height of about 6 feet. I'm only concerned here with the y-axis information over time, so I pulled that information from Tracker and posted it here. Then I used Python to create a model to predict the position of that wadded up piece of paper over time, using Newton's second law, which says the change of momentum of a system is equal to the net force acting on the system times the duration of the interaction. So for Model 1, my assumptions are that the net force is equal to W, where W equals the weight force or the gravitational force. The formula in Python looks like this. G is the universal gravitational force, which is 9.8 meters per second squared, and J hat is a vector 0, 1, 0. I plotted that information here, and then I compared the results. Orange line is the observation position over time, and the blue line is the model position over time. You can see that the model over-predicts position over time because it doesn't include the drag force. We were also asked to look at velocity over time. Here you can see velocity over time is linear, and it is increasing because of the force of gravity is 9.8 meters per second squared. So it increases over time. In the second model, I have the same assumptions for gravity, but I'm now going to add in FD, which is my drag force. And the formula in Python looks like this, which is B times the velocity of the object's vector squared. And I did this because there is a positive correlation between speed and drag on an object. So the faster the object is going, the more drag it's going to have. B represents a drag coefficient. In this case, it equals 0027, and I determined that through experimentation. So I plotted the model data here, and you can see I have the model is better in predicting the position of the object. However, it underpredicts where the object is. I feel I need a better representation of drag. There are many elements of drag, but the two biggest ones are the speed of the object and the cross-sectional area of the object. If I could calculate that, I could add that into my model and I'd probably get a better estimation. Also, I think I might have some video distortion in my model. In looking at velocity over time for Model 2, you can see it's not linear, it's a curved line, and it's beginning to flatten out at the end. Terminal velocity is approached as the velocity slope, the slope of this line flattens out. In this case, I don't reach terminal velocity because my observation period is too short. Had I dropped this object from a higher distance, it may have reached terminal velocity and in my observation. We were also asked to look at two scenarios where the object is lightly thrown instead of dropped, so that the initial velocity is faster. And then we were asked to look at another scenario where the object is thrown hard, and so the initial velocity is much faster. The top line is where the ball is lightly thrown, and the bottom line is where the object is thrown very hard, and this is velocity over time. So with the object that's thrown very hard, you can see the velocity initially is very fast, and then it slows down as it reaches terminal velocity. The object that's thrown very lightly has a faster initial velocity compared to where we dropped the object, but again, it reaches terminal velocity given enough time. And that is due to the relationship between drag and speed. So as objects speed up, the drag begins to offset the force of gravity. That is the conclusion of my video. I hope it was educational, and I look forward to your comments. Thank you.